Hello everyone, and welcome back. In today's tutorial, I'll show you how to integrate Retrieval-Augmented Generation, or simply RAG, into your ChimerAI application. We'll build a complete RAG pipeline from scratch, configure the AI service, index documents, query a vector database, switch between OpenAI and local Ollama models, and finally, customize the generated responses using prompt templates. By the end of this video, you'll have a fully functional, document-aware AI assistant that can answer questions based on your own knowledge base instead of relying solely on its pre-trained knowledge. Let's get started. The first thing we need is a new ChimerAI application. Open your terminal and run the ChimerAI create command. For this tutorial, we'll use SQLite as our database. When the feature selection appears, choose the RAG feature and continue with the setup. Once the project has been created, navigate into the application directory. Now run the installation script. This script installs all required dependencies and initializes the database. Depending on your machine and internet connection, this process may take a few minutes. Before we continue with the installation, let's briefly understand how the RAG pipeline actually works. Retrieval-Augmented Generation combines two different components. Instead of relying only on the language model's training data, the system first searches a knowledge base for relevant information. Only after retrieving the most relevant documents does the language model generate its final answer. This allows the AI to answer questions using your own documents, manuals, company knowledge, or any other custom data without retraining the model itself. To make this possible, every document is converted into something called an embedding. An embedding is simply a numerical vector that represents the semantic meaning of a piece of text. Documents with similar meanings produce vectors that are located close to each other in vector space. This is where FAISS comes into play. FAISS is a high-performance vector database and similarity search library developed specifically for this purpose. Instead of searching for exact words, FAISS searches for similar meanings. Within milliseconds, it finds the document chunks that are most relevant to the user's question. These retrieved chunks are then passed to the language model as additional context before the final response is generated. This combination of embeddings, vector search, and large language models is what makes Retrieval-Augmented Generation so powerful. Now let's configure the AI service that performs all of these tasks. The AI service is the heart of our RAG pipeline. Whenever a document is uploaded, the service splits it into smaller text chunks. Each chunk is converted into an embedding vector using an embedding model. Those vectors are then stored inside a FAISS index. Later, when a user asks a question, the exact same process happens again. The question itself is converted into an embedding. FAISS searches for the most similar document chunks. Those matching chunks become the context for the language model. Only then does the model generate its final answer. This allows the AI to answer questions about your own documents instead of relying only on its general training knowledge. To make all of this work, we first need to configure the AI service. Open the .env file inside your ChimerAI project. Let's go through the most important environment variables. The AI service URL tells the front end where the Python-based AI service is running. By default, the service listens on port 8002. Below that, you can optionally configure API keys for cloud providers such as OpenAI, Anthropic, or Azure OpenAI. These values simply act as fallback credentials. Later, you'll be able to manage AI providers directly through the dashboard without editing the environment file again. If you prefer running everything locally, simply configure the Ollama base URL. Once this value is set, the AI service automatically recognizes that Ollama should be used and adds the correct provider prefix whenever necessary. The next group of settings controls embeddings and the RAG pipeline itself. The default embedding model defines which model converts text into embedding vectors. For this tutorial, we'll use the OpenAI embedding model. It's important to understand that embedding models and chat models serve completely different purposes. An embedding model converts text into numerical vectors. A chat model generates natural language responses. Always make sure you're using the correct type of model for each task. Another important parameter is embedding dimension. Although you can specify this value manually, you usually don't have to. When the AI service starts, it automatically sends a test request to the configured embedding model. It measures the size of the returned embedding vector and configures the correct dimension automatically. Only if this automatic detection fails does the service fall back to the value stored in the environment file. The parameters embedding timeout seconds and embedding batch size control how embedding requests are processed. These settings become especially useful when working with slower, locally hosted models. Next comes RAG-min score. This value defines the minimum similarity score required before a document chunk is considered relevant. Chunks below this threshold are ignored and won't be passed to the language model. Finally, default chat model defines which language model generates the final answer after the relevant context has been retrieved. For this first example, we'll use OpenAI models for both embeddings and chat generation. Once you've saved the environment file, we're ready to start the AI service. Now that the configuration is complete, we're ready to start the AI service. Open a second terminal inside your ChimerAI project. Navigate to the service/AI directory. Before starting the service for the first time, we need to install all required Python packages. Simply install the requirements. Once the installation has finished, start the AI service. The service is now ready to receive document uploads, generate embeddings, build the FAISS index, and answer RAG queries. Next, let's start the front-end application. Once it's running, open your browser. We're now ready to test our complete RAG pipeline. Log in using the default administrator account. Open the RAG page from the navigation menu. The RAG interface consists of two tabs. The first tab is used to upload documents into the vector database. The second tab is where we'll ask questions about those documents. Everything starts by importing knowledge into our system. For this demonstration, we'll use a relatively small document containing information about Napoleon Bonaparte. Of course, the system supports uploading multiple documents in different formats. Simply drag and drop the document into the upload area. The AI service immediately begins processing the file. It extracts the text, splits it into smaller chunks, creates embeddings for every chunk, and finally stores everything inside the FAISS vector database. After a few moments, the indexing process is complete. Our knowledge base is now ready to answer questions. Now comes the interesting part. Let's ask our first question. We'll begin with something simple. Within a few seconds, the system generates an answer. Notice that the interface doesn't only show the final response, it also displays exactly which document chunks were retrieved from the vector database. Alongside each chunk, you'll see its similarity score. This makes the entire retrieval process transparent and easy to understand. Now let's try a more challenging question. Again, the system searches the vector database, retrieves the most relevant information, and produces the correct answer using the retrieved context. So far, everything works exactly as expected. But what happens if we ask a question that definitely cannot be answered using the uploaded document? Let's try one. Interestingly, we still receive matching results. This behavior is one of the characteristics of retrieval-augmented generation. The reason lies in the mathematical properties of embedding vectors and similarity calculations. Even completely unrelated questions may still produce a best match because vector search always tries to find the closest available embeddings. Explaining the underlying mathematics would go far beyond the scope of this tutorial. However, it's important to understand that this is a general property of embedding-based retrieval systems rather than a limitation of ChimerAI itself. Fortunately, in this example, the language model recognizes that the retrieved context doesn't actually contain the requested information. Instead, it tells us that it has to rely on its own pre-trained knowledge. This is certainly better than pretending the information exists inside our knowledge base. However, you shouldn't rely on this behavior in every situation. Different language models may react differently. Some models are much better at identifying missing context than others. As you'll see in a moment, not every model behaves the same way. This video isn't intended to be a deep dive into RAG theory. Its goal is to give you a practical introduction to retrieval-augmented generation and show how easily it can be integrated into your own ChimerAI applications. Now let's see what happens when we replace the OpenAI models with locally running Ollama models. Now let's repeat the same experiment using locally hosted Ollama models instead of OpenAI. To do that, we'll update our configuration. Open the .env file once again. This time, replace both the embedding model and the chat model with Ollama models. If you're unsure which models are available on your machine, simply run the command Ollama list. This displays every model currently installed. On this machine, 2 models are available. We'll use one for generating embeddings and the other for chat responses. Enter the model names into the appropriate environment variables. One small detail is worth mentioning. The Ollama/prefix is actually optional. Whenever Ollama_base_URL is configured, the AI service automatically detects that Ollama is being used and adds the provider prefix if it's missing. In this tutorial, we're specifying the prefix explicitly because it makes the configuration easier to read and understand. After saving the configuration, restart the AI service. During startup, something interesting happens. You'll notice that the embedding dimension has changed. Previously, our OpenAI embedding model generated vectors with 1,536 dimensions. Our Ollama embedding model now returns vectors with 768 dimensions. Even though we never changed the embedding_dimension value manually, the service automatically detected the correct vector size. This is one of the advantages of the automatic startup validation. You don't have to look up embedding dimensions yourself. The service determines them automatically. There's another important safety feature. Whenever the detected embedding dimension no longer matches the existing FAISS index, the service automatically rebuilds the index from scratch. This prevents technical errors caused by incompatible vector sizes. Of course, rebuilding the index also means that all previously uploaded documents must be indexed again using the new embedding model. Keep in mind that this automatic protection only works when the embedding dimensions are different. If 2 embedding models happen to produce vectors with exactly the same dimension, the service cannot detect that the model itself has changed. In those situations, it's a good idea to clear the index manually before uploading your documents again. That ensures consistent retrieval results. Since the FAISS index has been recreated, our knowledge base is currently empty. Let's upload the Napoleon document once again. The AI service now generates completely new embeddings using our local Ollama embedding model. After indexing has finished, we're ready to repeat the same questions as before. Let's begin with the same question we asked earlier. Immediately, we notice something interesting. Unlike the OpenAI embedding model, the Ollama model doesn't seem to retrieve any matching document chunks. That's surprising because the information definitely exists inside the vector database. Instead, the language model generates a detailed answer using what appears to be its own training knowledge rather than the uploaded document. Let's try another question. Again, the response contains information that wasn't retrieved from our vector database. And for our final question, it's clear that the answer comes entirely from the model's internal knowledge rather than from the indexed documents. This comparison highlights an important point. Different embedding models can produce very different retrieval quality. The effectiveness of a RAG system depends not only on the language model, but also on the quality of the embedding model used for vector search. One final note. For the sake of simplicity, this starter kit doesn't include model-specific embedding optimizations. Some embedding models, including Nomic Embed Text, which we're using here, can achieve even better retrieval quality when text is pre-processed with specific prefixes or formatting. Those optimizations belong to more advanced RAG tuning and would go beyond the scope of this introductory tutorial. If you're planning to use this system in production, that's definitely one of the first areas you should explore. You'll find additional comments inside the embedding function explaining where those optimizations can be implemented. Finally, let's take a look at prompt templates. Prompt templates work exactly the same way in RAG as they do in the regular chat interface. We'll create a simple template that controls the format of the generated answers. If you'd like to learn more about prompt templates, be sure to check out the dedicated videos on this channel covering the chat functionality. For this example, we'll create a template that always formats the answer as a list containing exactly 5 bullet points. Save the template. Now let's return to the RAG page. Select the newly created prompt template. Ask the same question again. As you can see, the retrieved information remains the same. The only difference is how the language model presents the final answer. Instead of a normal paragraph, the response now follows the formatting rules defined in our prompt template. This makes it easy to standardize answers across different use cases while still benefiting from Retrieval-Augmented Generation. And that's it for this tutorial. You've now built a complete Retrieval-Augmented Generation pipeline inside your ChimerAI application. Along the way, you've learned how to configure the AI service, connect cloud and local models, generate embeddings, build a FAISS vector database, upload and index your own documents, retrieve relevant context, compare different embedding models, and customize responses using prompt templates. Although this project is designed as a starter kit, it already demonstrates the core concepts behind modern enterprise AI systems. From here, you can continue experimenting with different embedding models, fine-tune retrieval parameters, optimize chunking strategies, and extend the system with your own data sources. I hope you found this tutorial helpful. If you did, please leave a like and subscribe to the channel. I'd also love to hear your feedback, so let me know in the comments what you'd like to see next. You can learn more about ChimerAI at chimerai.dev. And if you have questions, suggestions, or feature requests, feel free to contact us at contact@chimerai.dev.
I was buried in tabs in a half-built dream. Too many prompts and a broken machine. Then you showed up on my late-night screen. A clean little spark where the noise used to be. Got the models ready, got the code in place. Less time wrestling, more time making waves. From a rough first draft to a launch day glow. You gave me the road and I took it home. Je t'aime, ChimerAI. You make it easy. Tell my digital toolkit, big heart right in my side. APIs humming through the quiet of the night. Every test that passed felt like a win. Built a better future from the mess I was in. When the doubts come crawling in, you help me build again, step by step, line by line. You make the future mine.